the unit step function is the discontinuous function that looks like this. And it's 0, it's constant 0 for every value of time less than 0. And it's a constant 1 for every value of time greater than or equal to 0. So 0 is the place where it makes a unit step. And in Desmos, here's how you can graph a discontinuous function. I think this is really important because you're going to want to see what you're going to want to see the solution to your ODE. So you start with open curly bracket, or maybe you start with y equals, and then you start with the open curly bracket. And then you say, I want x less than 0 to be 0. So you use a colon to designate what the output of your function is going to be. And then for x greater than 0, or you could write greater than or equal to, it honestly doesn't matter. We want this to be 1. And we want to name our function u for unit step function, and it's a function of x. We write u of x equals that in Desmos. And then reset the view here. This is what it does. All right, everybody's on board. Now, if I wanted to move this unit step function so that the step happens at a time besides t equals 0, what I would do is I would have u of t minus some value c. Whenever I make minus c happen in the argument, that's going to translate where the step happens. So if I want it u minus 2, then the step happens at t equals 2. Okay? So subtracting a constant from the argument moves it to the right. Adding a constant from the argument would move it to the left. All right. So we're on the same page. Find the following Laplace transform. Clearly show every step of your work. So we want the Laplace transform of the unit step function where the step happens at a time c. And for this Laplace transform, we're going to remember the definition of what it means to be a Laplace transform. And that is an integral from 0 to infinity of e to the power negative st f of t dt. And this time, my function is the unit step function, t minus c. And this is equivalent to taking an integral from c to plus infinity of just e to the negative st. Take a moment to appreciate that. Because if t is less than c in my unit step function, then the value is equal to 0, and 0 times anything is 0. So I'm taking an integral of 0 in the integrand, and that adds nothing to my integral. So if I just start my integral at c for the lower bound, then I'm starting at the point where the unit step function is equal to 1, and 1 times e to the negative st is just e to the negative st. Everybody feels good about that? So then we take the antiderivative of e to the negative st, and that's going to be 1 over negative s times e to the negative st, and you plug in the bounds. We take the limit as t approaches infinity, and then we plug in t equals c, and then we subtract what we get. If t approaches infinity and s is greater than 0, then e to the negative st approaches 0. And then if I take t equals c, this is minus negative 1 over s e to the negative sc. So in other words, it's 1 over s e to the negative sc. You got it right, because in my notes, or on your handout, it should say e to the negative cs over s, or something like that. Same thing. Okay, questions? You see where the Laplace transform comes from? It's kind of weird. But that's what we get. Find the following Laplace transform. Clearly show every step of your work. So same thing. We've got the unit step function this time times another function. And that function could be anything, right? This is an abstract sense of like the lowercase f function could be any other function that has a Laplace transform. So what happens if I multiply the unit step function times another function and I take the Laplace transform? That would be the integral from 0 to infinity of e to the negative st times u of t minus c times f of t minus c dt. And so, just like before, this is the same thing as taking the integral with lower bound starting at c, because everything between 0 and c is just going to be 0, so we don't need to bother adding that up. And then after, when t is greater than c, the u unit step function is just a 1, and so this simplifies. And then I would like to do a w substitution, because I've already used the letter u. And we'll say w is equal to t minus c. And that means t is going to be w plus c. And this becomes the integral from 0 to infinity. It's 0 because I got to plug in the c in my formula for w. And by the way, dw and dt will be the same. And then I get e to the power negative s times w plus c times f of w dw. And then I see something like e to the negative sc, or e to the negative cs, and that's just a constant with respect to w. And then I'll have this left over. So, of course, we have e to the negative cs, and what is that improper integral right there? This improper integral right here is the Laplace transform of that lowercase f function. So all together, the Laplace transform of u of t minus c times f of t minus c is e to the negative cs times the Laplace transform of the f function. Remember, capital F denotes the Laplace transform of the lowercase f. And we're just saying for any lowercase f function, if the argument is t minus c, just take the Laplace transform like you would normally do of lowercase f of t, and that is the capital F of s part. And then to handle the whole unit step function and the shift in the argument, that both is taken care of by multiplying by e to the negative cs in the s domain. And again, that's on your little table, so you already have that in your handout. But this is how you find that Laplace transform. When you were asked to find the Laplace transform, this is the work you would need to show. Any questions about this? Okay. The unit pulse function with a duration of 2r is defined like this. We're going to use a lowercase d to represent the unit pulse function, and the 2r is a little subscript that tells you how long the duration is. And it's like this. I'll show you it on Desmos. This function is 1 divided by, and I can't use r on Desmos because it thinks, well, I could use a capital R. It thinks lowercase r is a radius, a distance from the origin in polar coordinates. And so I have to use a capital R. But it's 1 over 2r for negative r less than x less than r. It doesn't think d is a good name for a function, so let me name it f. No? Oh, I need to make it equals, not less than or equal to. Maybe I can use d. Now what it does not like. Oh, it has to be an x. There we go. Okay. This is my unit pulse function. And so obviously it's constant, and it only applies for a certain domain. Outside this domain, it's equal to 0. So maybe this is a better picture of what it looks like. It's 0 everywhere except for in this little patch where it's a constant positive number. And notice I choose the height of this constant little patch so that the shaded red area here has an area of 1. Yeah, so right now it has a height of 1/2, but it has a width of 2, so the rectangular area is 1. If I raise the width to 4, then the height shrinks down to 1/4, and now the area is still 1. And also, if I were to shrink my area down to like 1/2, or sorry, if I shrink the width down to 1, the height goes up to 1, and as I make the width smaller and smaller and smaller, the height has to keep shooting up because it wants to keep the entire area equal to 1. So I can have a bunch of different pulse functions, but for a unit pulse function, the integral is 1. No matter what the width is, the height adjusts so that the integral is 1. Okay? So it imparts a unit pulse. So like I said, one important property of the unit pulse function is that regardless of r, the integral is always 1. And since that's true for any value of r we select, any r greater than 0, then that means the limit as r approaches 0 of the integral is also 1. So imagine the smallest width that you can possibly imagine. Imagine a width of 0.000000001. If your width is 1 billionth, then the height of the function would be like 500 million or something like that, right? It's going to be a huge number, super tall. But still, the integral of the function would be 1. This limit, as r approaches 0, is called the Dirac delta function. So we're going to use the lowercase Greek delta to represent the Dirac delta function. And the deal with the Dirac delta function is it's equal to 0 for every time t that's not 0. But right at t equals 0, something happens so that the integral of the Dirac delta function is still equal to 1. And that something that happens is called an impulse. And the idea of an impulse is like, what if I had a spring hanging from the ceiling, and on the end of the spring I have like a 2-pound dumbbell, and so it's just kind of bouncing around. What if then I take a hammer and I smack the dumbbell, right? Like, how long does the hammer make contact with my dumbbell? Only like a billionth of a second, right? Like, it's an extremely short period of time, but it still imparts some force, right, to the dumbbell, right? You can see it in the way that the dumbbell's oscillation on the spring changes. So that's what we call an impulse. It's like a quick inelastic collision. Is it inelastic or elastic? It's been a really long time since I took physics.
Yes.
Yeah. Is the right word elastic or is it inelastic?
Inelastic would be like they stick together.
Inelastic is when they stick. So I'm looking at an elastic collision then. Yeah, any elastic collision, like two pool balls smacking against each other, would be an example of an impulse. So it happens so fast that it's not even meaningful to talk about how long the collision takes. So the Dirac delta function imparts a unit impulse, and if I subtract a constant from the argument, that just changes the time at which this impulse happens. That's the idea of the Dirac delta function. So now we might want a Laplace transform of the Dirac delta function, and this one is a little bit trickier to find. It's going to involve taking a limit, but if I want the Dirac delta impulse to happen at a time c, then this Laplace transform is going to be the same as the limit as r approaches 0 of the Laplace transform of the unit pulse function with a duration of 2r at t minus c. And then we're going to switch colors and just consider this Laplace transform. What would that look like? The Laplace transform of the unit pulse function with duration 2r would be the integral from 0 to infinity of e to the negative st times my function and let's assume that c is greater than 0. As long as c is not negative or c equal to 0, this would make sense. But since our integral has lower bound 0, if I want to capture the whole unit pulse, I've got to have a c value greater than 0 where that pulse happens. And so doing that, this is the same thing as 1 over 2r times the integral from c minus r up to c plus r of e to the negative st dt. So I'm getting rid of the rest of the interval of integration, except for the part where the pulse function is not 0, because if the pulse function is 0, then who cares? The whole integrand becomes 0. This is the only part that matters, is c minus r up to c plus r, and the value of the pulse function in this interval is 1 over 2r. That's a constant, so you can take it outside of the integral. And then you can take the antiderivative of e to the negative st. That antiderivative is negative 1 over s e to the negative st. And you want to evaluate that where t is equal to your upper bound, c plus r, and t is equal to your lower bound, c minus r, and then subtract. And so I can pull out the 1 over s. And then with the minus sign thrown in there, it's like negative e to the negative st. Oh, except for t is now c plus r. So negative s, c plus r, minus negative e to the negative sc minus r. And these have a common factor. This is e to the negative cs times e to the negative rs, and this is e to the negative cs times e to the positive rs. So e to the negative cs is a common factor. And since this is positive, I'm going to write this one first. And this one is minus e to the negative r. Wait, that's positive, because two negatives make it positive, and then we'll throw that 2 in there. The part inside the parentheses now is the definition of I forgot an s. Sorry, that might be confusing you. I need to multiply by s, right? But this is the definition of sine hyperbolic of rs. Pretty good. Pretty good so far. Now we got to remember that what we're actually trying to find is not just this Laplace transform that we figured out down there, but also we're taking the limit as r approaches 0 of this Laplace transform. So now let's take the limit of that thing as r approaches 0. And heck, if you're not super comfortable with the sine and the cosine hyperbolic, maybe that doesn't even help. Maybe we should just leave it alone. Let's see how it plays out if we just leave it alone instead of making it sine, cosine, hyperbolic. The sine and the cosine makes it slightly easier if you take those derivatives and you happen to know the values of sine and cosine, but Maybe it's also easier if you just leave them as e's, because those are easy derivatives as well. So if I take the limit as r approaches 0 of this whole expression, 1 over 2rs e to the negative cs times e to the rs minus e to the negative rs, I could first of all take everything that doesn't include an r out of the limit. Like I might write 1/2 e to the negative cs times the limit as r approaches 0 of e to the rs minus e to the negative rs divided by rs. And what happens as r approaches 0? I've got e to the 0 minus e to the 0. So it's a 1 minus 1 is 0. And as r approaches 0, the denominator also becomes 0. So I've got 0 divided by 0. Remember your calculus 1? This is an indeterminate form, so we can use L'Hopital's rule. And L'Hopital's rule says this is the same thing as the limit as r approaches 0, where I just take the derivative of the numerator and denominator separately. I hope you guys learned L'Hopital's rule in Cal 1. It's an important part. And so we take the derivative with respect to r because we're taking the limit with respect to r. So we take the derivative with respect to r and we get s e to the rs plus, because two negatives make a positive, s e to the negative rs divided by the derivative of the denominator is s. Now, what is this limit as r approaches 0? We have all of these s's cancel, right? So it's just e to the 0 plus e to the 0, which is 2. That limit is 2. And then the 2 and the 1/2 cancel, and we get e to the negative cs. That means the Laplace transform of the Dirac delta function, where the impulse is imparted at time t equals c, that Laplace transform is e to the negative cs. The Dirac delta function is also sometimes called the impulse function, because that's where it puts an impulse into your system. But that's how we ended up with the Laplace transform. Do you guys have any questions about that line of reasoning here? You don't have to know about hyperbolic functions. If you notice, I was able to do it without hyperbolics. You just need limits, you need L'Hopital's rule, a little bit of tricks. So let's work an example of what it would look like to have a discontinuous non-homogeneous term. And sometimes in the sense of like physical applications or engineering applications, we call the non-homogeneous term the forcing function. Because in like physical systems like that spring mass system, this is imparting a force onto your system. And this function, 1 minus a step function, would look like this. Because a step function is where it's 0 until you hit time t equals c, and then it steps up to 1, and then it continues. But if I have 1 minus a step, then it starts off at 1, and then at time t equals c, it goes down to 0. So that's what's happening. This system is kind of getting some force applied to it continuously up until some time t equals c, and then we stop applying the force abruptly. So let's see what it does in Laplace transforms. We're going to say take the Laplace transform of everything. And the Laplace transform of the unit step function is, I don't know, we just found it a moment ago. By the way, I forgot the Laplace transform of 1 isn't 1. It's actually 1 over s. And then the unit step function has Laplace transform e to the negative cs, 1 over s. So we got to solve for capital Y. This is just algebra. We're going to have 1 over s minus e to the negative cs, 1 over s, plus sy0 plus m0, all divided by s squared plus 4. Okay, what did we do? The 1 over s term, when I divide by s squared plus 4, it goes to this. The e to the negative cs stuff happens like this. And then notice when it has sy0, I pulled the y0 out in front because it's just a constant multiple. And then I remember s over s squared plus 4, that looks like one of my Laplace transforms. I can't remember if it's sine of 2t or cosine of 2t, but it's on your handout. And then notice I did m0 divided by 2 times 2 divided by s squared plus 4 because 2 divided by s squared plus 2 squared is one of your Laplace transforms. I don't remember if it's cosine of 2t or sine of 2t, but you don't have to remember. You'll have the table on your test. And then I'm almost ready to take inverse Laplace transforms, except for this and this, I need to do partial fraction decomposition. Because after partial fraction decomposition, that's going to become one-fourth times 1 over s minus s over s squared plus 4. I'm just telling you the answer, but when you do this partial fraction decomposition yourself, the way you would set it up is you would set it up like this. You'd have to have a constant over s for that factor. Plus, since this is an irreducible quadratic, you'd actually need what? bs plus c. You need that linear form over my irreducible quadratic. And then you would solve for a, b, and c, and you'd find that a is equal to 1, b is -1, and c is 0, if you solve that. Okay, so having done our partial fraction decomposition, we would then have capital Y, my Laplace transform solution, is going to be 1/4 times 1 over s minus 1/4 times s over s squared plus 2 squared minus e to the negative cs times 1/4 1 over s minus 1/4 s over s squared plus 2 squared. It's the same thing, but with the e to the negative cs in front of it. Plus y0 s over s squared plus 2 squared plus m0 over 2 times 2 over s squared plus 2 squared. Now, let's take the Laplace transforms and we'll get our time domain solution. One-fourth times 1 over s, and the inverse Laplace transform is 1/4. The part that says s divided by s squared plus 2 squared, that's going to be cosine of 2t. We'll handle this part last, so I'll have y0 cosine of 2t. And then I'll also have m0 over 2 times sine of 2t over here for that inverse Laplace transform. And then this part that has e to the negative cs in there. I don't have the table on me, but if you look up in your table, what is e to the negative cs times a function? This is one we discovered together today, on like page 3. If I have e to the negative cs times some capital F of s, what I do in the inverse Laplace transform is I take my unit step function of t minus c times what would have been the inverse Laplace transform, but I change the argument to t minus c. So the way this looks in the end is going to be u of t minus c times what would have been the inverse Laplace transform of this, which is 1/4 minus 1/4, and this would have been cosine of 2t, but now it's going to be cosine of 2 times t minus c. This is my solution back in the t domain. And maybe there's some ways you can simplify this. Like you could say, why not minus 1/4 times cosine of 2t and just combine those terms. You could also factor out the 1/4 and put that in front of your unit step function if you want to. But let's take a look at what the solution looks like in Desmos. It's going to take a minute to type it all out, but we're going to have y equals 1/4 plus y0 minus 1/4 cosine of 2t plus m0 divided by 2 times sine of 2t So I captured everything except for the unit step part. And then we're going to have minus 1/4 unit step times something there. Before I forget, unit step is going to be where x is less than 0, 0, x greater than 0, 1. And I need to make sure my t's are actually x's in Desmos and not t's. Desmos does not like the t's. And then on the inside of that unit step function, it was 1 minus cosine of 2 times t minus c. Oops. Okay. So if I set x equals c, this point is now the place where my input changes, my forcing function changes. And that means, like, look, we can change the what do you call it? The initial value, where the green curve crosses through the y-axis. Change my y-intercept. We can change the initial slope to be steeper or 0 or negative, right? So the y0 and the m0 work properly. The part I want to show you is this. If I change the location where I put in that unit step, it changes how the solution behaves after that point, but not before that point, right? Before this point, there's a constant force going in that's lifting the solution a little bit. And then after that point, remember, we removed the force away from my forcing function. And so the curve looks different when it doesn't have any kind of stimulus going in. You notice the peaks are not as high. And so, I don't know, I think it's kind of neat to be able to change the point where you make that discontinuity in Desmos and see how it wiggles the graph around. Anyways. Okay. So that's something you can do. Do you have any questions about how you do this? Okay. Let's do an example with our impulse function, the Dirac delta here. Solve the following ODE and IVP. So we are going to Laplace transform this thing. And notice that my forcing function is just an impulse of magnitude 5 at t equals c. So it's going to go along at 0. It's supposed to be completely flat at 0 until time t equals c. And I'm going to whack it with an impulse that imparts 5. And the height of this function is like technically infinite in a way because, right, it has like 0 width, but it still has an area of 5. But anyways, there's not really a way to graph this. It's just some impulse that happens at time t equals c that imparts a force of 5 total. Now, we'll have s squared y minus sy0 minus m0 plus 2sy minus 2y0 plus 5y equals, and then the Laplace transform of the Dirac delta function was just e to the negative cs. And this is going to be 5 times e to the negative cs. Yeah. Okay. now we solve for capital Y. And solving for capital Y means we have 5 e to the negative cs. I'm going to add sy0. I'm going to add m0, and I'm going to add 2y0. And I'm going to divide by s squared plus 2s plus 5. And then now it's going to be 5 e to the negative cs times 1 over Is that an irreducible quadratic, or can I factor it? It's irreducible. Okay. In the case when it's irreducible, we're going to want to do completing the square to this so that we can take a Laplace transform. And when I do completing the square, it's going to look like s plus 1 squared plus what? 4. And you might also preemptively write 2 squared, right? Because 4 is 2 times 2. And also, whenever we take the inverse Laplace transform, that's going to clue you in that this constant, which I think is called b on your table of Laplace transforms, is going to be the number 2. Next term, we have plus y0 times s over s plus 1 squared plus 2 squared. And then next term I have m0 plus 2y0 times not s, just 1 over s plus 1 squared plus 2 squared. Now, what I remember from your table of Laplace transforms is that this, when I have s over s plus 1 squared plus 2 squared, I really need this numerator to be s plus 1. If you have your table out in front of you, can you verify that like it should look like s plus a divided by s plus a squared plus b squared? And if you don't have your table, maybe you should pull it out and look at your table. You need to be familiar with using it for your next test. So what I really want is for this to be plus 1 in the numerator. And then over here, what I really need this numerator to be is 2. Because it needs to look like b over s plus a squared plus b squared. So I can get a 2 in the numerator over here if I'm willing to divide this by 2, right? That balances out, 2 divided by 2. And then I can get a plus 1 in the numerator here if I'm willing to subtract y0 times 1 over s plus 1 squared plus 2 squared from this thing. And you know, I think I should do that first before I do the 2 stuff, just so that I don't get too confused over here. Because if I subtract one of these y0s times 1 over all this stuff, that's going to balance out the plus 1 I'm doing right there. Let me rewrite it. And this is going to be m0 plus y0 times the 1 over s plus 1 squared plus 2 squared. Okay, now I can go ahead and multiply this by 2 and divide this by 2. And this way I don't get as confused. But does everybody feel comfortable with how we found this plus 1 by subtracting a y0 over here? And now we're in good shape to take an inverse Laplace transform of everything. And in the inverse Laplace transform, this is going to be 5 times. And what happens when I multiply by e to the negative cs is we get the unit step function at t equals c times what would have been the inverse Laplace transform, which is like e to the t times, oh shoot, hold on. What do I need to do here?
Multiply by 2, divide by 2.
Yeah. And this is sine or cosine? I think it's sine when there's a constant on top. So this is e to the t sine of 2t. But instead of just plain t, we also have to put in t minus c. That is because it's part of having e to the negative cs. Not only do you multiply by the unit step function, but you also shift the argument. So every time I see a t, I have to write t minus c in the inverse Laplace transform. And then the next term is going to be plus y0, e to the t cosine of 2t.
The s plus 1 doesn't do anything for that.
The s plus 1 part is where I'm getting e to the t, but I've actually made a mistake. If you look closely at that table, it shouldn't be e to the t, it should be e to the negative t. You're right that your table says e to the at, but the a you're expecting to see is s minus a here. The table looks like s minus a squared. And so if I see s plus a number, then that means I take the negative of this number, and so the a is actually negative 1. It's like s minus negative 1. And so I should have e to the power negative 1 t. And then I also have to add m0 plus y0 divided by 2 times sine, times e to the negative t times sine of 2t. But yeah, if you have to do completing the square, and completing the square gives you something like s plus 1 squared plus 2 squared, then s plus 1 is like s minus negative 1, and that becomes this e to the negative t factor. So completing the square is going to give you an exponential factor in front of your trig function.
Does the first 5 have a 2 underneath it?
Yes. Good catch. I forgot when I multiplied by the 2, I should have also changed that in my solution. All right, I think that's it. So let's take a look at what this would look like in Desmos. What does a impulse look like? 5 over 2 unit step, e to the negative t over c, etc. Times sine of 2t minus c plus y0 e to the power negative t cosine 2t plus m0 plus y0 over 2 e to the negative t sine 2t. Oh, sorry, I've switched from x's to t's. So I got to go back and x my t's. All right, so in green, notice this is the solution. Let's double check and make sure my y-intercept works correctly. Seems like it works. Let's make sure my initial slope works correctly. It seems like it works. So I get this green solution for some initial value and some initial slope. And then I'm going to whack it with a hammer at time t equals c. And so, like, depending on where I hit the thing with my hammer, it's going to change what happens after that point. Right? So imagine the y coordinate is like the vertical position of my dumbbell that's hanging from the ceiling on a spring, and so it's bouncing up and down. And then as it's on its downward trajectory, I hit it with the hammer really hard, and so then it, bam, after that point, shoots up again, continues oscillating after that. That's what an impulse does. You can notice, by the way, if you were to name this function f of x on Desmos, and then you also wanted to graph its derivative, you just have to type in y equals f prime of x. And what's nice is about your solution is that it's a continuous solution. You want your solution to be continuous because your mass is not going to teleport from one coordinate to another. But you can see that the derivative is not continuous. So like the vertical velocity of my mass does have a discontinuity where it gets smacked by the hammer. That kind of makes sense. That's how it should be. There's actually a step change in the velocity. Okay. We probably don't have enough time to finish this example, but let's talk about what the forcing function is going to look like, and we'll see how far we can get. This forcing function, notice, is like a unit step times a line. So before the time t equals c, it's going to be 0 because of that unit step factor. And then we hit the time t equals c, and at the time t equals c, this linear factor is still 0. But as t becomes greater than c, it's going to increase like that. So this is sometimes called a ramp function. It's 0 up to a point, and then we start ramping up the input force. By the way, another reason you might want to model a discontinuity in a differential equation, besides like smacking weights with hammers, is if you were an electrical engineer and you're trying to model some circuit as a second order differential equation, you might want to know what would happen if you had like an arc failure. What I mean is like air is a really good insulator. Air does not conduct electricity very well, except for in the case of like lightning strikes. Because in a lightning strike, the electric potential difference gets to be so great that it ionizes the air molecules, and the ionized air does conduct electricity. And this also happens with like super high voltage circuits. Like if you're using an air gap as an insulator between a large difference in voltage, what could happen if there just gets to be a little bit too much voltage is the electricity will arc across the gap. and close the circuit. And when that happens, suddenly you've got like an impulse of a massive current right into your system. And so you also might use the Dirac delta function as an electrical engineer to kind of figure out, like, do a what if analysis. What if we have this capacitor fail? What if the insulator we're using in our capacitor just suddenly fails and closes the circuit? What's going to happen after that? And maybe you even design a circuit like this. I remember talking to a physics professor like 10 years ago, and he was setting up an experiment where he needed like a really high energy laser for just like a fraction of a second, like a millionth of a second or whatever. So he was designing a circuit that had a big capacitor in it. The capacitor would store up a lot of electric charge, and then he would suddenly close the circuit by just like lowering a switch. And as soon as the circuit closed, there was this huge impulse of voltage, and then it went away almost instantaneously. So if you want to know what's going to happen to your circuit components, you can model it dynamically using a ODE and a Dirac delta forcing function. Okay, but let's do this with the ramp. We've got s squared capital Y minus sy0 minus m0 minus 2s capital Y plus 2y0 plus capital Y equals, and this is the tricky part where you'd have to consult your table of Laplace transforms. If I just had the Laplace transform of the boring linear function t, that Laplace transform would be what? That would be a constant. The Laplace transform of a constant is k over s. But this time we have the variable t.
Would it be 1 over s squared?
Perfect. The Laplace transform of t to the n power is n factorial divided by s to the power n plus 1, right? That's what you see in your table. But in our case, we just have t to the 1 power. 1 factorial is 1, and 1 plus 1 is 2. So the Laplace transform I would need is 1 over s squared. But I don't just have t. I have this t function modified, so I'm subtracting c from the argument, and I'm multiplying by a unit step function. And the Laplace transform of a unit step function times another function where I shift the argument by subtracting c is e to the negative cs times what would have been the Laplace transform. That's also something we found earlier here, right? So now I'm going to write on the right-hand side as my Laplace transform e to the negative cs times 1 over s squared. See how we got that? Then when we solve for capital Y, we keep e to the negative cs 1 over s squared. And we're going to add to that sy0, add m0, subtract 2y0. And we divide by s squared minus 2s plus 1. So that quadratic factor is as s minus 1 squared. And split things up. For this, we will need to do partial fraction decomposition. This does not need partial fraction decomposition. This one's good to go. And this one is good as well. Pretty sure. No, I'm wrong. You have to do partial fraction decomposition. The reason I'm wrong is this one. This one's actually fine, but this one's not good to go, right? Because in this partial fraction decomposition, you would have to set s over s minus 1 squared equal to a constant over s minus 1 plus a constant over s minus 1 squared. And you would only end up with constants in the numerator after that. You would actually get rid of the s here through partial fraction decomposition. The one over on the right is good because I already have just a constant over s minus 1 squared. And so if I tried to set up this partial fraction decomposition, b would be 1 and a would be 0. But in the case where I have an s in the numerator, it's not the same. And then this is going to be a crazy partial fraction because if I have 1 over s squared times s minus 1 squared, this is going to need to be a divided by s plus b divided by s squared plus c divided by s minus 1 plus d divided by s minus 1 squared. Because that's how repeated factors work in partial fraction decomposition. So this would be a long problem just because you got to do partial fractions twice. All right, so now you can see kind of the benefit of doing Laplace transforms is that before, with variation of parameters, we could do some interesting forcing functions like tangent. But even though Laplace transforms can't do tangent or secant or anything like that, they can do step functions and ramps and impulse functions. You get stuff that's a little bit exotic in its own way.